Welcome to Chemistry Lab. Today's lab, nuts and bolts. And I do mean actual nuts and bolts. You're going to be putting together units of nuts and bolts and using that to study stoichiometry. Stoichiometry is about the mathematical relationships within chemical equations. For example, if we look at a reaction of nitrogen plus hydrogen to make ammonia, in a balanced chemical reaction, we need coefficients in front of each of these. Let me pay attention. We need 2 of these and 3 hydrogens in order to have a balanced reaction. And one way to look at a balanced chemical equation is to say that the coefficients, the numbers in front, right, the big numbers in front, represent the number of molecules that are reacting with each other and the number of molecules of product that form. For example, we could say that 1 molecule of nitrogen, draw a little picture here, 1 molecule of nitrogen reacts with 3 molecules of hydrogen, right, where all of these are hydrogen atoms, to make a total of 3 molecules of hydrogen to form 2 molecules of ammonia. And we can think of this on the individual molecular level, right? 1 molecule to 3 molecules forming 2 molecules. But we can also scale this up because the coefficients represent a ratio. So we could talk about 100, for example, 100 molecules of nitrogen reacting with 300 molecules of hydrogen to form 200 molecules of ammonia. Or scale it up further and say 1 million molecules of nitrogen reacting with 3 million molecules to make 2 million molecules. You see what I mean? Now, in the world of chemistry, remember that Avogadro's number is a very important number, right? 6.02 times 10 to the 23rd. Very large number of things. And that's equivalent to what we call 1 mole of substance. So we could scale this up in terms of moles. We could say 1 mole of nitrogen, which means Avogadro's number of nitrogen molecules, would react with 3 moles of hydrogen, which would be 3 times Avogadro's number, to generate 2 moles of ammonia, or 2 times Avogadro's number. We're going to take this same idea to look at nuts and bolts. Our reaction will look something like this. 1 bolt plus 2 nuts. Put the little nuts on the bolt, and we have 1 unit, which will be a bolt nut 2, right? So this represents the bolt by itself, this represents the 2 nuts by themselves, and then you screw them together and you get this 1 unit that we've got a 1 in front of this, right? That's a single unit that is a bolt with 2 nuts. And in the lab, we're going to look at this ratio, but we're also going to be relating it to mass. In a laboratory, we have a balance to weigh things out. And in stoichiometry, where we're concerned with the mathematical relationships within chemical equations, we look at this ratio of how many things, how many counted out things, reactants or products, are being used or formed, but we have to relate that to how much things weigh. Because in the laboratory, that's what we do, we weigh things out. Now, molar mass is the relationship between how much something weighs and how many things there are. In other words, the units of molar mass are grams per mole, right? Mole representing how many there are, grams meaning how much we weigh out. So we're going to look at that in terms of our nuts and bolts reaction. You're going to be able to weigh out the bolts, weigh out the nuts, and look at the relationship between their masses and the ratios that are needed to react with one another in a balanced equation. And then we're going to extrapolate that idea back to chemical reactions. We can talk about how much of these different species we weigh out, and therefore how much of any product should form. At the end of the lab, there's a more challenging problem that goes into stoichiometry. There's a balanced chemical reaction that you're using, but there's some other conversion factors that are part of that problem. And I want to kind of give you a head start with that as well. You're looking at a scuba device self-contained breathing apparatus. It operates at a rate of 40 liters of air per minute. And I'm writing it this way just to remind you that 40 liters of air per minute could be described as 40 liters of air equivalent to 1 minute of time. And that means that you can use this as a conversion factor to convert liters of air to minutes or minutes to liters of air. Another piece of information that you're given in that problem is that exhaled air contains 4% carbon dioxide by mass. 4% CO2 by mass. Now what that means, well, percent means parts out of 100, and so we've got 4 parts of CO2 out of 100 parts of air, and because we're describing mass, those parts will be in grams. In other words, we've got 4 grams of CO2 equivalent to 100 grams of air. Once again, this is a conversion factor. It will allow you to convert grams of CO2 to grams of air, or grams of air to grams of CO2. The last piece of this problem involves density. Density is given as 0.0010 grams per milliliter. And remember that that means 0.0010 grams equivalent to 1 milliliter. Once again, also a conversion factor that you could write this way, 0.0010 grams equal to 1 milliliter. And this is for air. So this allows you to convert milliliters to grams or grams to milliliters. So using these 3 relationships and the balanced equation that's given in the problem, you can solve even more complex stoichiometry problems. I think that's everything you need to know for the lab. Have a great lab.